Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. Martin Sukara is a postdoctoral scholar at UC Berkeley. His research interests in quantum computation, including quantum error correction and quantum algorithms. He has been working on the development of new quantum error correcting codes that have a high error correction threshold and can be efficiently decoded. There's a long bio. He's done a lot of good stuff, and we're thrilled to have him here. Martin?
Thank you for the introduction. Today I'm going to talk about quantifying the resources needed to do real-world computations on a quantum computer using the topological and concatenated error correcting codes. Quantum error correction is, of course, a very important problem. We cannot build a quantum computer without it. And also it's a challenging problem because it's different than classical error correction, where if we have classical information, we have just bits of zeros and ones. And the only error that can occur is a bit flip. But quantum information is continuous, and we have a new range of partial errors, but also phase flips and phase shifts that we need to error correct. The two main families of quantum error correcting codes that can address these errors are the concatenated codes, which were developed starting with the work of Peter Shor in 1995, and topological error correcting codes, which started with the work of Alexei Kitaev in 1997. Both of these code families have some advantages and disadvantages, and these are summarized in this table. The topological codes have much higher error correction threshold, which means they can tolerate much higher error rates. And also, computation with the topological codes can be done using local operations. For concatenated codes, if we, for example, want to do the 2-qubit controlled knot operation, we have to typically swap qubits before we can perform a local controlled knot operation. But for topological codes, we can use braiding, which can be done purely by using local operations, and no swapping is needed. But topological codes, they have to solve a difficult problem to decode the errors. Typically, a minimum weight matching problem is used to guess which error occurred given syndrome information. But for concatenated codes, the decoding is much simpler. So the classical controller that controls these error correcting codes is a bit more involved for topological codes. Also, it is not clear which code is better in terms of number of qubits, number of gates, and in general the resources. And this is the focus of this talk. I'm going to address the issue of quantifying the resources needed to do error correction with these two code families. And also I will look at some ideas I have about simplifying the decoding for the topological code. So this is the structure of the talk. First, just some background about concatenated and topological codes. Then I will lay out the methodology that I use to quantify the resources needed to do error correction with the two code families. And finally, I will speak about building a faster decoder for decoding errors in topological error correction. The stabilizer formalism is very useful to characterize error correcting codes. The stabilizers are basically the syndromes we need to measure to diagnose errors. They are generated by the stabilizer group, which the elements of the stabilizer group pairwise commute. And the stabilizers act trivially on the code space. So if we have a state psi, which is in the code space, then the stabilizer doesn't change the state, which means we can safely measure these syndromes without affecting the encoded information. And we can learn about errors from these syndrome measurements. Concatenated codes, perhaps the simplest example of a concatenated code is the Bacon-Shor code, which is the quantum analog of the classical repetition code. where we encode each bit 3 times, and then we use a majority vote to decide whether we encoded 0 or 1. So to encode a logical state 0 in the Bacon-Shor code, we need to also protect against the phase flip, not only bit flip, but also phase flip. So to encode 0, we use the 3 plus states, and to encode 1, we use 3 minus states initially. And then to protect these pluses and minuses against bit flips, we use the repetition code. So 0 would become 000, and 1 would become 111. So as the name suggests, concatenated codes have concatenated structure. So we can repeat using smaller building blocks. We can build the code from ground up. And up to a certain limit, this will improve the error correcting properties of the code. Decoding of errors with concatenated codes is very simple. In case of the Bacon-Shor code, it's basically just simple majority voting with the stabilizers. What is often cited as advantage of these concatenated codes is transversal nature of many of the gates. So what does this mean? If a gate is transversal or operation is transversal in the code, then we simply need to apply the gate n times for each of the n building blocks in the code. So for example, the controlled NOT operation is transversal. So we have these 2 blocks of 9 qubits each, which represents 2 logical qubits. And to perform the controlled NOT operation, we need to do control NOTs between the corresponding pairs of qubits. But actually, from the resource estimation perspective, even though this gate is transversal, it is fairly expensive because we cannot generally do controlled NOT operations on a physical quantum computer between any pair of qubits. They have to be located at the same location. They have to be neighboring qubits. So that means we have to use the swap operation to move the qubits around. And this is one reason why using concatenated codes is expensive. And then, of course, we also have gates that are not transversal. So it is possible to show that we need at least some non-transversal gates to do universal quantum computation with the concatenated codes. So here's an example of the T gate, which is non-transversal in the Bacon-Shor code. So the gate uses an ancillary state that needs to be distilled. This is the distillation circuit, which takes 15 copies of the ancillary state T+, and it distills a single copy of the ancillary state with higher precision. And this distillation process needs to be repeated sufficient number of times to achieve the target fidelity of the ancillary state. And then the ancillary state is used in this circuit to apply the T gate. So the original state psi was here. Here was our ancilla. And after this circuit is applied, the T gate is applied to the state psi, which appears here. Topological quantum error correcting codes have a very different structure. They consist of qubits that live in a regular grid. In this picture, this is the surface code of Denis, Kitaev, Preskill, and Landau. The qubits live at the edges of the grid, and the stabilizers, which are shown in this picture, we have two types of stabilizers, the stars here and the plaquettes. And by measuring these stabilizers, we can obtain error syndromes, which gives us information about the errors that occurred. There are other examples of topological quantum error correcting codes. This is the 5-square code that I developed at IBM. Each code has a little bit different properties. One of the key advantages of this code is that in order to reconstruct the syndromes, we only need to do 2-qubit measurements. So the red objects in this figure are the stabilizers, but they decompose into smaller gauges. And by measuring gauges of weight 2, we can reconstruct the syndrome information. And this can be beneficial in situations where weight 4 entangling measurements are too expensive to perform on certain quantum technologies. In addition to locality, another advantage of the topological codes is the way they perform computation. Computation can be done by braiding. Control knot operations can be done by braiding. So how does this work exactly? Well, the Pauli operators, logical X and logical Z, are strings in the lattice. So here is the basic lattice, which doesn't contain any defects, which means that the syndrome measurements are enforced in the entire surface of the lattice. And this lattice, in this state, encodes 2 logical qubits. And this picture shows the logical X and Z operators corresponding to these 2 logical qubits. Now let's say we want to encode more qubits, and we want to perform control knot operations in this system. So what do we have to do? Well, it turns out that if we puncture a hole in the surface, we will increase the number of logical qubits that are encoded. So first of all, what do I mean by puncturing a hole? Do we have to change the physical layout of the system? And the answer is no. To puncture a hole, we simply stop enforcing the measurements of the stabilizers in the region where the hole appears. So this is the hole, and we don't measure any of the stabilizers in that region. And if we introduce 2 such holes, a pair of holes, that will represent 1 logical qubit. And this is easy to see because the logical X and Z operations will be strings that connect the pairs of defects and strings that loop around the holes. Now, which string is X and which string is Z depends on the exact location of the hole in the lattice, because there are 2 kinds of holes, rough holes and smooth holes. But regardless, to perform controlled knot operations in this system, we simply take one of the holes which corresponds to the controlled qubit of the C-knot operation, and we will move the hole to the target qubit. Then we braid the hole around the hole of the target, and we move it back. Now this works if the control is smooth and target is a rough hole. And there is a simple conversion circuit that can address the problem when we have both control and target qubits represented by pairs of smooth holes. So this is very convenient because this operation can be done simply by changing the location of the syndrome measurements. So there is no physical movement of information needed to do the controlled knot operations. And how do we decode errors that occur in these topological codes? Well, when we do our syndrome measurements, we will detect locations with non-trivial syndromes, which are shown in red color in this figure. So these 4 syndromes were measured as non-trivial syndromes. And then it is easy to see that these syndromes occur at endpoints of strings of errors. So if we have a string of X errors, then at the endpoint of the string of errors, there is going to be a non-trivial syndrome. The same for Z errors. There is this star syndrome here and here, which detects that there is this string of errors consisting of a single Z error here. So once we measure our syndromes, we can use minimum weight perfect matching to guess how these syndromes should be connected. You can use Edmonds Blossom algorithm, for example, to do this. And then once we connect the pairs of matching syndromes, we will correct. So this is the plaquette syndrome. This is also plaquette syndrome. So we know that if these syndromes are matched, we need to do X corrections, bit flips, on a string connecting the syndromes. So the red X's represent the correction that is being done, and the black X marks, they show the actual error that occurred. So in this case, After we apply error correction, we just apply this loop operator consisting of bit flips on this loop here. But it turns out this is fine because this loop is a loop that is in the stabilizer group, so it doesn't affect the encoded state of the system. Now, in reality, this matching problem is actually a three-dimensional problem because our syndrome measurement itself will be faulty. We need to use a quantum circuit to measure the syndromes, and that's going to be prone to errors. So some of the syndromes are going to show as faults even though there was no error that occurred, and vice versa. So to address this, we can use basically an analog of the 2D problem by introducing the third dimension. And here in the third dimension, each of these lines represents a single syndrome that is measured over and over again. And we will mark a red point if the syndrome measurement outcome is different than the measurement outcome in the previous round. And this way we will obtain a set of points in 3 dimensions that we can match. And now, depending on the error rate of measurement versus the error rate in the memory, we can adjust the weights of these edges in the temporal dimension compared to the weight of the edges in the space dimensions. And if we solve the minimum weight matching problem, then with high probability we will correct the errors that occurred. But this problem is, so this is a classical problem that the classical decoder has to solve, but it turns out if we have millions of qubits and we need to repeat the syndrome measurements a certain number of times, this is going to be a large problem that is going to be expensive on a classical computer. The surface code of course exhibits threshold behavior. So there is certain threshold. If the error rate is below the threshold, we can correct the errors that occur at this rate perfectly well, as long as the code distance is big enough. So as long as we have enough physical qubits encoded the information, we can correct the errors. If we exceed the threshold, we cannot recover the information. So I did a simple simulation that estimates the threshold for various topological codes. I used C++, and I did Monte Carlo simulation, so I will inject a random error into the system according to the probability model that is described here. And then I will try to decode the error, correct it, and I will record the frequency with which I can correct the errors at the given probability level after a certain number of Monte Carlo repetitions. And this is the result that will come out of the simulation tool. So here I varied the error rate with which I injected errors into the system, and on the y-axis is the percentage of the time that I can successfully recover from the error. And you can see that as I increase the distance of the code, so as I increase the number of physical qubits that encode the information, the curve in this picture will get sharper and sharper, which means if I am just below the threshold, the percentage of failures is going to be very small. So almost always I will be able to recover. And if I'm above the threshold, then the percentage of failures is large, so I cannot recover. But if I choose...
When you say the percentage of failures, you mean the ones that were not recovered?
Percentage of failures is the number of Monte Carlo iterations that resulted in failure, so I could not recover the original encoded state. And we can see that we need to choose code of sufficient distance if we want certain, let's say we want at least 5% probability of succeeding and our physical error rate is 3%, well then we need to choose code distance at least 8 to guarantee this performance. So the key properties of topological codes, it is easy to increase and decrease code distance, and that way influence the reliability of the resulting code. Local operations are sufficient to do controlled knot operations and basically computation with the codes. And they have error correction threshold that is significantly higher than threshold of concatenated codes. But the drawback is that the classical processing for error decoding is time-consuming. So next I'm going to move to the actual resource estimation with the topological and concatenated codes. First I'm going to give a brief overview of the properties of the quantum technologies that we considered as part of the quantum computer science project, and which form the base of this resource estimation. Then I'm going to show you the methodology that I used to quantify the resources needed to perform operations with the error correction codes and the numeric results. So this is the structure of the resource estimation task. We will consider a certain set of quantum algorithms, and for each of these algorithms we will express the number of logical qubits we need to perform the task, the number of logical gates to do the computation, and also information about parallelization factor and the length of the 2-qubit operations in the system. For the quantum technologies, we will consider the gate times and fidelities and the memory error rate on qubits that sit idle in the system. And we will also consider properties of the four basic families of error correcting codes: Bacon-Shor, Steen, C4C6, and the surface code. And all this information feeds into our resource estimation tool that produces a qubit layout, and it estimates the circuit delay, gate count, and the fidelity of the entire computation. Yes?
You say number of logical qubits, but that number probably depends on the input, right?
Yes, so we will choose a specific problem of a certain size, and then we will express this. So right now, we finished phase 1 of the QCS project where the problem sizes were hard-coded, but now we are moving to phase 2, and we are going to parameterize the problem sizes so that we can adjust a simple parameter which describes the size of the problem, and that way we can obtain gate counts. For example, let's say we want to run quantum computation for 1 year. What size of problem can we solve? So we can solve the inverse problem if we parameterize. And this is what we are working on right now.
And for a given size, you take the worst, the upper bound that you can get?
For a given instance of the problem, are we considering...
For a given size of an instance, that's what you said, right? You said parameter is the size of the input rather than input itself. Or maybe misunderstood you.
The parameter would be this. So let's say we want to solve some graph problem. We want to, let's say the triangle finding problem. We want to decide if there's a triangle inside of a certain graph. Then the parameter would be the number of vertices of the graph. So of course, the more vertices, the harder the problem is going to be, and the higher the gate count is going to be. So this is a collaborative project. I have been coordinating the work on the resource estimate on behalf of the USC team. This is the IRPA project. The resource estimation is currently being done by 4 teams independently. And I have a number of collaborators at a number of universities who all did great work to analyze the properties of the algorithms and quantum technologies. In our project, we are studying 4 families of error correcting codes: Bacon-Shor, Steen, C4C6, and surface codes. We have 7 algorithms, which all of these algorithms have very different qualitative properties. They use different quantum primitives. Some of them use quantum simulation, some of them use quantum random walk, fast Fourier transform. So it's a very diverse group of algorithms. And we are considering also 6 technologies and 6 quantum control techniques that enable us to reduce the errors in these technologies. And in this talk, rather than presenting the cross product of these results, which we had to obtain in the project. I'm just going to show the highlights of our results. So for the quantum technologies, our goal is to obtain, for a range of realistic quantum technologies, to obtain the gate times and gate errors to perform physical quantum gates in the system. And in the QCS program, we studied the effects of quantum control protocols on the gate errors, basically which control techniques are effective at reducing the gate errors and which are not. Regarding our methodology, we used Monte Carlo simulations to insert random noise and study the effect of control protocols on this noise. We used optimization tools to optimize choices of control parameters. And also, we used gate constructions because not all quantum technologies support all elementary quantum gates. And even if they do, sometimes smart decomposition of the gates from a different set of gates can result in a smaller error. So this is one technique we used as well. And this technique was actually very helpful in reducing some of the errors for some technologies. The two of our favorite technologies are superconducting qubits and ion traps. Superconducting qubits have errors that are due to Markovian noise, and therefore it is difficult to reduce these errors by using control techniques. The error of the gate is basically proportional to the duration of the gate, and if we use sophisticated control techniques that increase the duration of the gate, that will actually lead to increase of the error. So primitive control is the most successful with superconducting qubits. And the errors would be roughly 10 to the minus 5 for a quantum gate on average. Ion traps have extremely low error rates, except the measurement error. But we were able to use a circuit decomposition that uses 3 measurements to bring down the error of the measurement down to roughly 10 to the minus 9, which is in line with the low errors of the other gates for ion traps. So these are our 2 favorite technologies because they have low errors and they can be used both with the topological codes and concatenated codes. Neutral atoms also work reasonably well, or sort of well with topological codes, but the errors there are about 10 to the minus 3, so that's just below the threshold for topological codes, but they cannot be used with concatenated codes. And for quantum dots and photonics, our results currently do not allow us to use these with any of the existing quantum error correcting codes. So here is an overview of the numbers that feed into my resource estimation tool. So here are the main. I just selected some of the technologies: superconducting qubits, ion traps, and neutral atoms. And I'm showing the average gate time for the average operation. Our resource estimation tool actually takes the gate count for all the individual gates. So the information that feeds into the tool is more detailed than what this table shows. So this is the average gate time. Then we have gate error for each gate operation. And then we have memory error per unit of time per nanosecond. So the key observation here is that ion traps have the lowest error rates by far, but also the gate times of ion traps, they are not very short. They are roughly 3 orders of magnitude slower than the gate times for superconductors. So superconductors are faster, but they're a little bit more error prone. The errors would be 10 to the minus 5. So it is certainly interesting to compare these 2 technologies, because it's just by looking at this table, it's not clear which one is better. And then we have neutral atoms, which they're both slow and error prone, so they're not going to be certainly not going to be the winner among
On the other hand,
these.
the memory already is 0.
That is right, but I'm not convinced that well, this is unphysical. I think this is artifact of our model. So to do the estimation, I picked 3 quantum algorithms. I picked algorithms that will give us reasonable running time. So in our project, we are considering algorithms that have just quadratic speedups also, and these result in huge gate counts. We are considering running these algorithms on problem instances that are very ambitious. Again, this leads to big gate counts. So here I'm trying to handpick the algorithms and problem instances that will result in results that are human readable. So if we actually build the quantum computer, we will be able to see the result of the computation in a couple of months. So one such problem is estimating the ground state for a molecule. I picked a molecule that is not too difficult to analyze, so I picked this glycine molecule, small organic molecule, which only requires 50 basis functions to describe the ground state. And I decided to calculate the ground state in a fairly crude way with only 5 bits of accuracy. So this is the first problem.
Which basis was that? Which of the quantum chemistry bases did you use?
I'm not sure about this.
STO, 3G, 4G, A321, don't remember.
I'm not sure about this.
How many qubits do you require? You work differently.
50 qubits for the basis and then 10 qubits additional. The second problem is the binary welded tree algorithm. So the problem formulation is as follows. I will take 2 binary trees and weld them together in the middle. So here the top part is one binary tree. Here at the bottom is the second tree. The 2 root vertices are special. One of them is marked as the start vertex, and the other node, the other root is the finish vertex. And the goal is to start at the start vertex and find the finish vertex by relying on an oracle. And the oracle will give us information about the graph. If we supply the oracle with a label, a name of a vertex in the tree, it will give us the names of the neighboring vertices. And each vertex has actually exponential number of labels assigned to it, and the oracle will return just one of the labels. And we have to decide, once we query the oracle at a certain vertex, we have to decide which of the 3 neighbors we will move to next. And this way we have to find the finish vertex. And using classical computation, it was shown that it is impossible to find the finish vertex in sub-exponential time. But there is a polynomial time quantum algorithm that uses the continuous quantum random walk. And we chose this problem for 3 depth 300, which is an instance size that would be very difficult to do on a classical computer.
My question.
Yes?
So 3 depth is n equals 300. 3 depth.
There's the depth. So
There's a lot of nodes in the tree.
the number of nodes is going to be huge. It's going to be like, right,
It's a
exponential.
binary tree, it's 2 to the
And
six.
the-
2 to
Well, no, but it gets bigger and it gets smaller, so it's half.
3 trees are
No.
perfect trees.
Yes, well, they are not exactly perfect. There's this almost perfect. I think we can assume that they are perfect for this purpose. They're not perfect in the middle because it turns out there is this this strange feature of the problem. If we have exact binary trees and we weld them in the middle, we will have vertices of degree 2 in the middle, and then there exists a classical algorithm that can exploit this information. It knows basically when it hits the middle, and it becomes easy to guess at which point in the path we make the wrong turn. So they're scrambled a little bit, but they're basically binary trees.
So since you scramble a little bit, now there are many possible trees, right?
Many possible paths.
I mean, I think that this, you mean the center is a random cycle?
Right.
Yes.
Yes.
So now, so in addition to number of nodes, there is a which particular tree is used, a pair of trees. So what I didn't understand the first time around, how get a number which depends only on the size of the problem, when it also depends on particularities of
The permutation of the joining, of the
right.
welding.
Is this problem available in the public literature?
It is. There are at least 2 papers I'm aware of that study
You
this
could look it
problem.
up. It's the IARPA
Okay.
binary welded tree benchmark or something,
Okay.
and find out enough detail to.
Okay.
And then the third algorithm I studied is the triangle finding problem. So again, it's a graph problem where we have graph with n vertices, and there is our task is to decide if there is a triangle in this graph. So this is the instance of the problem is set up to be this pathological instance where the graph is dense, but there are very few triangles. There is going to be either one triangle or no triangle at all. And the task of the algorithm is to decide if we are given an instance of a graph that has one triangle or no triangle. So the triangle here is in the middle, and then we have these components which contain, each of them has n over 6 nodes. And these edges mean that all the vertices in the individual components all the pairs of vertices are connected by edges. So there is no triangle in this region, but a single triangle in here. So we consider it a graph with 2 to the 15 nodes.
So what's the challenge here? What's the classical way of solving it, if there is one?
Well, I guess classical way of solving it. There is an oracle also that tells you how the structure of the graph looks like. So I guess you have to query it. You have to tell it the name of the vertex again, and it tells you which are the neighbors, and then you have to scramble this information.
What size graph has been done classically? It's a better way to ask.
I believe that for this problem, 32,000 nodes is actually pushing the boundary, because this is the original parameter given by IARPA, and from phase 1, and they try to come up with parameters that are pushing the boundary. Yes.
And are we looking for like quadratic grower like speed up here, or what is the hope?
I believe the quantum walk here gives exponential speed up too.
Provably?
I'm not sure about provably. I know that for welded tree it's provable. For the triangle problem, I'm not willing to bet.
Polynomial number of triples of nodes. You can go through all triples of nodes. Just exhaustively in its polynomial.
Right, but I believe the oracle will. Oh, right. I will have to check the speed up claim for this algorithm. So this for the welded tree, it's exponential, and for tree depth 300, this would not be solvable classically. For the ground state estimation, this molecule. So we originally studied molecule that was more complicated, but actually the numbers, the gate counts coming out of that are huge. So I decided to analyze a simpler molecule, and for this molecule, this would be, I believe, classically solvable problem. So this table summarizes the gate counts that we obtained. So again, I picked the welded tree and triangle finding problem. They use the quantum random walk, which is fairly efficient. So the gate counts coming out are not too bad. And also for ground state estimation, we are using a simple molecule. So we have ground state estimation 10 to the 12 gates. The number of qubits needed to do the calculation, it's 60. These are the logical qubits. And then we have parallelization factors, which tell us on average how many of the gates can be done in parallel in the circuits. In my opinion, there is scope for improvement in these parallelization factors. We don't know if we can lay out the circuits in a better way that is more parallel. And for each of the algorithms, we not only have the total gate count, but we also have a breakdown by gate type. So this is the ground state estimation algorithm. So we know how many state preparations we need, how many Hadamard's, C-naughts, SZ gates measurements. And this is the information that feeds into...
Go back.
Yes?
You're able to do ground state without any rotations? Who derived the circuit? Maybe that's a better way to put it, that you used. You know where it came from?
Oh, so I think actually the Z rotations are arbitrary rotations. I think that's misleading.
Okay. Yeah. If it's arbitrary in Z, that's fine. There are some Z's, really.
Yes,
Okay.
that's misleading choice of.
Okay, that's fair. It's like you can't do that without rotations. Okay.
For the actual analysis of the error correcting codes, so what is the overhead? So far we only saw numbers with logical qubits and logical operations. What is the number of physical operations we need to do? So we looked separately at the 3 concatenated codes and at the surface code. So for both code families, we assumed a tiled layout. So we have a 2-dimensional structure that contains the physical qubits. And the structure is divided into tiles, where each tile is in charge of 1 logical qubit. The tile has enough space to include ancillas. So if we need to error correct the information in the logical qubit, we can do so within the tile. And the 3rd dimension in the space is reserved for classical control. So how exactly looks the layout of the qubits inside of the tile? We had to determine that separately for each of the error correcting codes because they encode information differently. Operations are done differently. And the number of qubits is going to differ inside of each tile too. So here is the tile structure for the Steen code at the 2nd level of concatenation. So the 1st level tile is here, so it contains 6 by 8 physical qubits. And then at the 2nd level, we use 6 by 8 of these level 1 blocks to construct the tile. And we have to choose a sufficient level of concatenation to guarantee high probability of success of the calculation. So I chose a cutoff 50% success probability for the calculation. And I used the equation, I believe it was originally shown by Gottesman in a paper, that shows how many concatenation levels we need. And from there, we can calculate the number of physical qubits. So what is going on inside of the tile during computation? Well, the size of the tile depends on the code. There is existing literature that shows us the optimal location of the qubits inside of the tile and the sequence of operations we need to do to perform error correction as well as all other logical operations. So existing literature tells us what to do for Steen and Bacon-Shor code. But for the C4-C6 code, we had to come up with our tile design. So here's a specific example from the paper of Swor that shows the operations inside of the tile for the Steen code. So the tile size is 6 by 8. And the Steam code, it uses 7 physical qubits to encode 1 logical qubit. So these red qubits here, the red locations, they're the locations where the data lives. And then here on the interior of the tile, we have some ancillas that are needed in order to do syndrome extraction and error correction for the Steam code. So this determines the location of the data qubits, the ancillas, and also a sequence of operations. So the paper of Swore actually shows the exact gate sequence of all the gates that need to be performed to do error correction as well as all other operations. This is a snapshot of the tile at a particular moment in time during the error correction. And these arrows, they represent physical gates that are being done. So these are swap gates and controlled NOTs. The layout has to be optimized to minimize the number of operations that need to be done to ensure good reliability of the circuit. And to minimize the amount of movement. So these swaps are done because controlled NOT operations can be only done on qubits that are next to each other. So this is actually a very expensive thing for the concatenated codes, the movement. Our tools, we used recursive equations to express the gate counts for the desired level of concatenation. So we count the number of elementary gates and the time we need to do these operations, taking parallelism into account. We also estimated the additional space that is needed to do ancilla state generation up to desired level of fidelity. We used similar methodology for the topological codes. So as I said earlier, in topological codes, pair of holes represents a logical qubit. So we assumed this layout. We have to ensure sufficient spacing of the holes because loops that connect the holes are logical operators. If we have holes that are too close to each other, there's going to be a low weight logical operator and the code is going to be error prone. So we calculated a code distance that is sufficient to again guarantee that the calculation succeeds with high probability. And we also took into account the movement of the holes during braiding. So we left enough space in between the holes so that another hole can be braided without affecting negatively the error properties of the code. So to obtain the physical qubit count, that is very simple. We just obtain the code distance and then we multiply. From code distance, we can get size of one tile and we multiply by number of logical qubits. And that gives us number of physical qubits. For gate counts, we started by first calculating the exact running time of the entire computation. And then from there, we were able to calculate the number of gates that are needed to do the error correction, which is done all the time on essentially all the qubits. So this is the major component of the total gate count. And then finally, we added the small number of additional gates needed to do gates such as measurements, Hadamard, and so on. So numeric results. These are the results for superconducting qubits, which, so if you recall, this is the technology that has very fast gate times. On average, gate only takes 25 nanoseconds. And as far as errors go, this is somewhere in the middle of the road. Among the technologies I showed you, it's 10 to the minus 5 error per logical gate for the worst gate. And this table shows the resources for the 3 algorithms for the instance sizes we discussed. So you can see that the surface code will result in computation times from months to years for these instances. Here are the gate counts, and then this is the physical qubit count. So we need a few million qubits for the computation. The Bacon-Shor code, which is representative of the concatenated codes, requires much higher computation time. And I think the reason is we need several levels of concatenation, 3 or 4 levels of concatenation to address the gate errors, and that will translate in a huge gate count and huge time needed to do the computation. And also, the number of physical qubits is going to be high because of all this concatenation. We need to store the information somewhere. Yes?
How sensitive is it to this number? Like if you push to 10 to the minus 6, would everything lose like 3 orders of magnitude in the results?
That is a good question. It is sensitive to it, but perhaps.
Say the question.
Oh yes, the question is sensitivity to the gate errors. If we change the gate error, will the resource requirement change a lot? And the answer is yes. It is sensitive because for concatenated codes, for example, there is this very sharp transition. If you go from 3 concatenations to 4 concatenations, the resource requirements will blow up by 3-4 orders of magnitude, perhaps. And that's by changing a single number. If you are just at the boundary, then this can cost you a lot. But also, what is very interesting, I'm going to discuss this in the next slide. Okay.
So in the ground state estimation, we sort of agreed here that you need to have various zero rotations as the gates.
Mm-hmm.
Right.
Yes.
Did you count them each one as a single gate, or did you estimate the kind of the length of decomposition into the implementable gates, like T gate, for example? In other words, does it represent a T count involved in the implementation of a single zero rotation on that?
Your Z gates 1 gate, or were they 100 gates, or whatever,
Right.
from Solovay-Kitaev equivalent?
Well, we use Solovay-Kitaev to do the decomposition.
Of the rotation?
You did.
Yes.
Oh, okay. Okay, so that is the real number of
Yes,
gates?
yes.
Okay.
Right. So what can I ask? What flavor of Solovay-Kitaev do you use? Yeah, I have a sinister
Yeah, of course.
Reason to ask this question. We kind of improved Solovay-Kitaev by 3 orders of magnitude recently, and I was wondering how much it would have affected the ground state part.
Possibly, I'm sure there could be improvements.
Wasn't a big count.
No, but he had Z up there was the full rotation gate. So
Understand.
when he goes into here, he has to multiply it by 10 to the second, 10 to the third to get the accuracy he
All
needs,
right.
even 5-bit
So
accuracy.
he didn't actually have the,
Right. So the point is you could probably drop 3 digits. The 10 to the 22nd might drop down to 10 to the 19th instead. If you didn't have to do if you could get 3 orders of magnitude better on the rotations. Is that what you're getting at?
Yes.
Yeah.
Yes, I would be certainly interested in learning new techniques to improve the decompositions.
It's still up at 10 to the 19th. I mean, it's still, it's a simple molecule and still a hell of a lot of gates.
Right, but
It's
we have
better.
lots of problem instances that have much higher numbers.
Yeah.
I'm just showing numbers that are human readable here.
Yes.
Again, along these lines, is it clear that if you drop, so you said you took 50% success rate for the complete algorithm. Is it clear that if you drop that to something like 10 to the minus 6 and you just repeated the experience like a million times, is it clear that it wouldn't be better than waiting for 1,000 years for one instance at 50% success probability?
That's a great question. We haven't done this calculation, and it's possible that we can obtain lower running time by targeting lower fidelity of the algorithm and repeating it a few times. Also, there are basically many optimizations that could be done, and we haven't taken into account. One such other optimization is distillation of the encelas. Perhaps if you distill them with lower, your target fidelity for the encelas is lower. Perhaps that will introduce inaccuracies, but since the distillation again is this concatenated process, if you use one fewer concatenation in the distillation process, that saves you a lot of time and a lot of gates. So it's possible that these trade-offs can improve the resource estimate significantly.
So In that earlier slide, did you have the logical gates and so on? I mean, how many, suppose there was no errors.
Was it this?
Yeah, that one.
Yeah.
That Z is really rotated Z, and has to be expanded out, that's all they can
I
do.
understand, so there
Right.
might be some big number in
Right.
there.
That gets much bigger.
Yes.
All the rest of them are sort of what they are, which says you have something on the order 10 to the 14th or something plus whatever the Z count, whatever the T count in Z is, and
Yep.
so an H count and so on. Yeah.
So the next question that I wanted to ask was if there is some regime. So we saw that the topological codes outperform the concatenated codes for the superconductors. So the next question I wanted to ask is there some regime where actually the surface codes are not performing as well? And the answer is yes. So I considered these three technologies, which we have neutral atoms, which have huge error rates on the gates. And then we have superconductors, which have lower errors. And then we have ion traps, which have even lower errors. Okay, so the result here is very interesting. For the high errors of neutral atoms, we can only use the surface code because the surface code meets the threshold 10 to the minus 3. But the concatenated codes, they just cannot deliver. In the regime where we had, the time to do the calculation is huge because the gate time for neutral atoms is 3 orders of magnitude slower than for superconductors. Superconductors, we already know that the surface code will win. But then if we decrease the error rate even further for the ion traps, the interesting observation is that the concatenated codes actually do better than the surface code. And the reason is, with these very small error rates, we only need one level of concatenation. So error correction with the concatenated code is super cheap. But the surface code, the duration of the computation is almost independent of the code distance, because all the operations in the surface code are done in parallel. All the syndrome measurements are parallelized. All the operations, the braiding, is highly parallel. So what actually determines the running time for the surface code is the duration of the gate. So some key observations: the surface codes are better in most regimes unless we are dealing with very low error rates. T and C0 gates are the dominant gates for logical circuits. But as far as physical gates are concerned, C0 was the most frequently used physical gate for topological codes, and swap is the most frequent gate for concatenated codes. And the reason is that for concatenated codes, we need to use swaps to move information around so that control node operations can be done locally, whereas surface codes do not need the swapping. So finally, I will just use the last 5 minutes to describe some thoughts about building a faster decoder for topological codes. So far we were only concerned with the quantum resources, but we have to keep in mind that for the surface code, we will also need a classical controller that decodes the errors that occur. So we know that we need to be able to solve a problem that has millions of physical qubits. We know that syndrome measurements will be inaccurate, so we will need to decode errors after several rounds of error measurements, syndrome measurements. And we know that we like technologies with low gate times, because the surface code works well with technologies with low gate times, such as superconductors. So we would really love to have a decoder that works in real time. And this is work that I'd like to do in the coming months. I started looking at the decoding problem. To decode errors for the surface code, we need to solve the minimum matching problem to match pairs of syndromes. And one key observation is, so even though this problem is polynomial time solvable, we would typically use the Edmonds matching algorithm to solve it. It is going to be too slow for the problem sizes we are considering. So one observation that is due to Fowler is that we don't need to solve the most general minimum weight matching problem, but we can prune certain edges from consideration. So here's an example. We have a vertex V, and we want to match it to some other vertex. And Fowler's observation tells us that points in space cast shadows. And if there's here point number 1, it will cast shadow here, and point 3 will be shadowed by it. So vertex V, we only need to consider the edge from V to 1, but we can ignore the edge from V to vertex number 3. And the reason being, we can show that assuming a minimum weight matching would use the edge from V to point number 3, we could find an alternate matching that would have lower weight. So now this is a two-dimensional picture, and of course we need to solve the problem in 3 dimensions. It turns out that in 2 dimensions there is a very simple linear time algorithm that can prune the edges, prune the shadowed edges, but I did not manage to find a counterpart in 3 dimensions, and in fact I believe it's unlikely that such algorithm exists. But I found a heuristic that that allows us to prune the edges in linear time with very favorable results. And the heuristic works as follows. So we are given the vertex V, and we want to find the candidate edges. So we will look in the 4 geographic dimensions for the closest point, and then we will create a bounding box in these 2 dimensions. And we know that any point that vertex V will connect to is going to be inside of this bounding box. And then we look at points in the 3rd dimension perpendicular to the screen, and we find the closest such point in each direction, and we connect vertex V to these points. So I looked at the resulting average degree of the vertex in the 3-dimensional graph that I obtained by simulating the surface code. And so here's the number of qubits in the surface code. So I went up from 100 qubits to 1 million qubits. And I looked at the average degree of a vertex after the pruning. And it seems that the number approaches about 180. So we have in the limit, we will have a constant number of edges per vertex. And I tried to solve the minimum weight matching problem on just my laptop computer and see how long it takes to do the matching. And these are the results. And you can see that the scaling is also linear. So for 1 million qubits, it takes a bit over a minute to construct the graph, generate the errors, and prune the edges. And then it takes about 7 or 8 minutes to do the matching itself. Yes, there's a question.
You've listed the number of qubits, but what is the error rate at which you're running your simulation? Because that has a big effect on the number of vertices you need to pass to the graph.
I was running fairly close to the threshold at about 2/3 of the threshold. If the error rate was much lower, then I think the result would be we could decode errors for higher number of qubits because there would be just fewer syndromes. But probably, I think the statistical distribution of the points in the space would be very similar. So I think the degree of the node would actually be the same. Yes, another question?
Performance of the decoder, because now you're using this heuristic to parallelize your algorithm, if I understand correctly. So
this is not parallel yet. This is.
But it can be.
But it can be, and I'd like to look at parallelization.
So now it's possible using this tree, right?
So it is certainly possible. I have actually parallel implementation. I think I have it in the next slide. I have a parallel implementation for the pruning, which is easier to do. I mean, the pruning is just a very simple heuristic. I don't have parallelization for the matching itself, which uses the Edmonds algorithm. It uses primal and dual updates for.
My question, does this trick of creating these blocks around the vertices and having these smaller graphs, does that affect the performance of the decoder significantly?
Oh yes, it's very significant. I would not be able to do. I would probably have to stop at somewhere between 1,000 and 10,000 qubits if I didn't do the pruning.
Sorry, I didn't mean in runtime. I meant in probability of errors, probability of decoding errors.
It doesn't affect the probability of errors because we are still solving the exact same problem. We can show that we only prune edges that must not be in the minimum weight matching. So in conclusion, I did some work on topological quantum error correction. I helped to develop 2 new quantum error correcting codes in this space, the 5 squares code and the triangular code. And in the past year, I worked on the quantum computer science project of IARPA to estimate the resources required to run a variety of algorithms on realistic quantum machines using 4 families of quantum error correcting codes. And currently I'm looking at the problem of parallelizing a decoder for topological quantum error correcting codes. Thank you.
Well,
Yes.
I don't know if there's a simple answer to this. If not, we can take this offline. But what about the bottom and top boundaries when you decode the surface code with faulty measurements? Can you take into account preparation errors? And what about the last layers of measurements? You have to kind of... Okay, so I guess the point is that you measure many times to be more sure about the syndrome outcome. But the last measurements you did might have errors which you're not sure are good. So you want to decode what is in the past in some sense. So how do you deal with this issue?
So I think there are 2 or perhaps 3 schools of thought how to deal with this. One of them says, well, just regardless how you solve this problem, you could just do a dummy round of perfect measurements and then run your algorithm on this instance. And then with the knowledge that in reality you would do something else, such as do the error correction maybe 10 rounds behind schedule, behind the actual measurements. The second school of thought would be obviously simulate exactly what would be going on in the real system, which is perhaps this. You would do the decoding with some lag. And the third school of thought is to use a periodic boundary condition in the time dimension. So you would connect essentially points to the boundary. Yes, Arvind?
So just a comment, because I think you collaborated with all 3 of us on this project, but
yes.
On the surface code estimate, we had some tiny numbers, and I just want to say that for some of the distillation procedures, we assumed a very conservative model of how we were distilling magic states, and so some of those numbers I think you showed could be reduced fairly significantly with a penalty in area relatively easy.
I changed that already, actually.
Oh, okay.
Right. So we had earlier results that were more pessimistic because we used a conservative assumption that only a single C-node would be done in the surface code at any given time. But the numbers I showed right now, I tried to parallelize all the C-nodes that I could, including in the state distillation.
Okay. Yeah, but in our state distillation, we
and yes, we need a larger number of qubits than originally predicted. That is correct.
Okay.
Thank you again.